Hello friends, and welcome to our very first video lecture for our honors chemistry course. Today we're going to start talking about measurement, specifically uncertainty and significant figures. Our objectives, we're going to understand what do we even mean by uncertainty when we're talking about measurements. We're going to express quantities, pieces of data, with significant figures and uncertainty notation, and then we're going to apply some rules, these magical things known as sig figs. You probably already know quite a few of these vocabulary terms. We use them outside of science. Today we're going to maybe tweak the definitions a little bit, make them super specific for chemistry. Uncertainty, not being certain. Significant, important. Accuracy and precision, sometimes we use these interchangeably outside of science. Today we're going to talk about how they are related, but actually quite different. And then just a quick review of place value. We learned this in math way back in elementary school. Do make sure that you know that to the right side of the decimal point, we have tenths, hundredths, thousandths, 10,000ths. It keeps going from there. We can call this the ones place or the units place, and then of course tens, hundreds, and it goes on from there. Do make sure you're thinking about those place values. They're super important when we're talking about our significant figures. But we're going to start with this idea, this concept of uncertainty. Literally, how uncertain are we about our measurement? Here I have a beaker. This beaker has purple water in it. This is my line for 100 milliliters. Here's my line for 200 milliliters. Up here, and it's kind of hard to see with the glare, 300 milliliters. So this line must be 250, halfway between 200 and 300 milliliters. How much purple water is in this beaker? How much purple water is in this beaker? Clearly more than 200, less than 250, maybe 220 or 215 or 225, somewhere in there. We don't know exactly because we don't have a line to tell us exactly how much water is in this beaker. And so this is the concept of uncertainty. I know that it's 220 milliliters-ish. Luckily in science, we have some super specific ways to denote what is that ish? And we show that ish with a plus minus sign. So this piece of measurement is telling us that something has a mass, because G's for grams, something has a mass of 24.3 grams, but the uncertainty is telling us that it's up or down by 1/10 of a gram. So it actually could have a mass as little as 24.2 grams. It could have a mass as much as 24.4 grams. It's not going to have a mass of 24.5 grams because that's outside our uncertainty wiggle room, but pretty close to 24.3, plus or minus 0.1 of a gram, up or down by that 0.1 of a gram. We can use our digital equipment and determine what the uncertainty is two ways. Number one, there's going to be a sticker somewhere on your piece of equipment that tells you what the uncertainty is. The other way for our digital equipment is that we can look at the measurement. The last digit, the last place value in our digital equipment is going to give us the uncertainty. So here, this 3 is the last place value. I'm going to count tenths. Notice the decimal place here. Tenths, hundredths, thousandths, 10,000ths. So that means that with uncertainty, I could write this mass as 0.4253 plus or minus 1/10,000th of a gram. This is going to be my uncertainty. And again, somewhere on this analytical balance is a sticker that's going to tell us that the uncertainty is 1/10,000th of a gram. Let's look at this one. I've got a thermometer here. Notice degrees Celsius. Our temperature is 36.4 degrees Celsius. What do we think the uncertainty is going to be? Again, because the equipment is a digital piece of equipment, we're going to look at that last place value and we're going to say it's going to be one of those. So my temperature here, I'm going to write with uncertainty as 36.4 plus or minus, that's a tenths place, 1/10 of a degree Celsius, which means that the temperature could be anything between 36.3 and 36.5 degrees Celsius. Here are 3 more pieces of digital equipment. This is a thermometer. It reads 30.6 degrees Celsius. Here is a scale. It's 412 grams. And then here we've got another scale. It's 500.0 grams. Pause the video, or in the Ed puzzle, go ahead and determine how you're going to write each of these measurements with uncertainty. Let's look at answers super quick before we move on. Hopefully you had 30.6 plus or minus 1/10 of a degree Celsius, tenths place. Here, our last place value is the ones place. So we're going to have 412 plus or minus 1 whole gram. And here, again, we've got a tenths place. So we're going to have 500 plus or minus 0.1, a tenth of a gram. But what if I don't have digital equipment? What if instead I have what we call analog, which means that there's no display. There's nothing telling me what is the volume of this beaker. I'm going to have to use my eyeballs and my brain to figure that out. This is a beaker. I'm going to have 2 options once again to figure out what is the uncertainty now looking at this analog equipment. The first, we're going to look at the label of our piece of equipment. Often, somewhere on the glassware, you're going to have an uncertainty label. Maybe it'll say plus or minus 25 milliliters. Maybe it'll say plus or minus 10%. You're going to have either an actual volume, in this case with the beaker, or a percentage telling us what is the uncertainty. Use that if it is printed on your beaker. However, if there's not already an uncertainty printed on the label, what you're going to do is figure out the increments between the graduations. Graduations are the lines on your piece of equipment. So here's a graduation, here's a graduation, here's a graduation, and they keep going up and up and up. What we're going to do is figure out the increment, how many milliliters between each of those graduations, each of those lines. So if this is 100 and this is 200 and there's a line between, this must be 150, which means that our graduations, the increments are in 50 milliliters. What we're going to do to determine the uncertainty is we're going to take that increment between the smallest graduations, the smallest spaces between the lines, we're going to divide that in half. 50 divided by 2 is 25 milliliters. That means that the uncertainty of this beaker is plus or minus 25 milliliters. So I'm going to look at this guy and I'm going to be like, that's like 220 milliliters. Plus or minus 25 milliliters. That's a really big-ish. That's a lot of wiggle room. But beakers aren't great for measuring volume. In fact, we're not going to choose to use them to measure things. We're using our beakers mostly just to mix, to heat, to stir. A much better choice for measuring is a graduated cylinder, literally sometimes called a measuring cylinder, because it's so good at measuring, and it's good at measuring because it has so many graduations, so many lines. This particular graduated cylinder does have the uncertainty labeled on it, plus or minus 5 milliliters. I know it's kind of hard to see on the screen, but it's plus or minus 5 milliliters. What about this graduated cylinder? I know you can't tell if there's a label or not because I zoomed in. Let's pretend like there's not a label. We're going to have to figure it out on our own. So here we have the line for 6 milliliters, and here we have the line that is labeled 8. Halfway between 6 and 8 must be 7. I notice that there's 1, 2, 3, 4 lines between 6 and 7, which means that each of the spaces has a value of 0.2 milliliters. So from here, 6.0, 6.2, 6.4, 6.6, 6.8, 7.0. So each one of these has a value of 0.2 milliliters. That means that our uncertainty is going to be half of that, or 0.1 of a milliliter. What, though, is the volume in this graduated cylinder? I'm going to erase some of my scribbles so that you can actually see the volume of the water in this graduated cylinder, and notice that it does a little bit of a dip-de-doo. This is known as the meniscus. The meniscus is formed because water is polar. It's attracted to the glass. the inside of the graduated cylinder. So what's our rule about measuring with the meniscus? Do I measure the top, this one top? Do I measure the bottom? Our rule is we're going to measure the bottom. So we're going to look just about here-ish. Okay, good. I know it's not, I struggle to draw the straight lines with my drawing tablet, but we're going to make it work. So again, here I have my 6.0, 6.2, 6.4, 6.6. This is just a smidgen above 6.6, so maybe I'm going to say it's like 6.61 milliliters plus or minus 0.1 milliliter. Super duper. We have our value, we have our uncertainty. We're going to do a quick check for our decimal places because I want the decimal places here, the place values, to match the place values here. I have a hundredths place. I only have a tenths place. So what I'm going to do is actually throw a 0 in here so that the last place value of my measurement and my uncertainty match. I'm still saying we've got some wiggle room of about 1/10 of a milliliter, but it's actually closer to 10 hundredths of a milliliter, which is almost the same thing, but this has a little bit more specificity than just 1/10 of a milliliter. So this is our measurement. This is the volume in the graduated cylinder, 6.61 milliliters plus or minus 0.10 milliliters. Let's do a couple more. And here's another graduated cylinder. I'm going to have you determine what is the volume, including uncertainty, of the liquid in this graduated cylinder. Go ahead and pause the video or answer the question in the Ed puzzle. Even though I'm showing you again, here's a whole entire graduated cylinder, because the label for this one is cut off, you're going to have to use the smallest increment divided by 2 method to determine the uncertainty. Hopefully you noticed that this line for 20 and this line for 30, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines in between. And so that means that each one of the lines is 1 whole milliliter. 20, 21, 22, 23, 24, 25. Here's 25 and here's 26. And we're going to measure from the bottom of the meniscus. And it looks to be a little closer to 26 than 25. So let's estimate 25.8 plus or minus, what's half of 1? That would be 0.5 of a milliliter. This, or something close to 8, is correct. It doesn't have to be 8. It could also be 7. What it cannot be, friends, though, is 25.817243. That doesn't make any sense. We can't even know that. So don't get excited and start adding extra digits. We're going to take what we know and then add just one more digit. We know for sure 25 point something. We're going to estimate that 8, and that's going to also include the uncertainty. Feeling good? Let's do one more. This piece of equipment is super cool. It's called a burette. We can also spell it without the last T-E. We can also call it a titration burette. All of those names are correct. What's cool about our burettes, a little bit different from our graduated cylinders, is that the numbers go in the opposite direction. Here at the top of the burette, it's a 0. Here at the top, it's a 0. How these guys work, we actually fill them with a liquid. So we're going to have liquid all the way down. And then we're going to turn this nozzle, it's called the stopcock, and liquid is going to drip out of the burette. It's going to drip out. And as it drips out, that top level is going to go down, 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 down. And then when we're done releasing the liquid, we're going to turn the stopcock again. The level is going to stop moving, and then we can read. So here, let's look at the burette zoomed in. I have 20, I have 15. So there's 15. This must be 16, 17, 18, 19, and then here's our 20. Notice that I have 10 little lines between each and every one of our big numbers. So each one of our increments is 0.1. We're going to divide that in half to find our uncertainty. 0.05 milliliters is going to be the uncertainty for this burette. Here's where things get tricky. So here's 15, here's 16, here's 17. Our liquid is just a little bit above 17. Does that mean it's like 17.05? No, because 17.05 would imply that we're getting closer to 18. So we actually have on the other side closer to the 16, which means that we have a little bit less than 17. And so our best answer is going to be like 16.95 plus or minus 0.05 milliliters. Let me erase the scribble so that you can see that a little bit more closely. Here is our 17 line. Notice that the liquid level is just slightly above the 17, but that doesn't mean more than 17. It actually means less than 17 because we're counting down. 16.95 plus or minus 0.05 of a milliliter. So let's pause with the measuring devices and talk super quick about two vocabulary words, accuracy and precision. Again, outside of science, they kind of mean the same things: to be accurate, to be precise. These are both good. They're also both good in science, but they have slightly different connotations. Accuracy for us in science is how close a value is to its actual or accepted value. Are we getting the answer that we're supposed to be getting? Are we getting the measurement that we're supposed to be getting? The other word, precision, is actually how close the measurements are to each other. Of course, the ideal is to have both accuracy and precision in your data. That's this target. Our numbers are where they're supposed to be, and they're also close to each other, high accuracy and high precision. Sometimes we can have great precision. Those values, those data points are super close to each other, but they're, oh my gosh, so far off of where they're supposed to be. We don't have the correct, the accepted values, but we do have values that are being repeated. Probably something's wrong with our scale, or we don't know how to use our titration burette, but we're doing it the same way over and over, but we're doing it wrong way, the same way over and over. We can also have values that are pretty close to the accepted value, but they're kind of spread out. High accuracy, low precision. Of course, worst case scenario, whoa, I don't even know what's going on with that data. This is not what we want. When we choose equipment in our investigations, the goal is high accuracy and high precision. If you needed to measure the volume of a liquid for an investigation, are you going to choose a beaker or a graduated cylinder? Which one's going to give you higher accuracy, higher precision? Hopefully you're going with that graduated cylinder. Beakers are great for mixing, for pouring, for heating, for stirring. Graduated cylinders, not super great for stirring or heating, but they are magical for measuring volume. We can talk about the accuracy and precision of our equipment. We can also analyze our data for accuracy and precision. Let's say here that I was looking at density of pieces of aluminum, and I did 3 different trials, calculated density for these 3 different pieces of aluminum, and I got pretty close values. I'm feeling pretty good about my precision. We have some high precision. Those densities super close to each other. But do I have accuracy? The accepted density of aluminum is 2.7 grams per cubic centimeter, and I got kind of significantly more than that. And so we're going to say high precision, low accuracy. We're here. We got the same thing over and over, but we didn't get what we were supposed to get. There were some sources of error in our investigation. Our scale wasn't calibrated. That means that it was measuring incorrectly every time, or we were doing something else wrong. We were doing it wrong the same way over and over, which is why we got that precision, but something was definitely wrong for us to have such low accuracy. Quick vocab check here. Define accuracy and precision. Hopefully you remember that accuracy is all about getting values, data points that are close to the accepted or actual values, whereas precision, you're getting data points that are close to each other. And let's do one final check with uncertainty. Here's another graduated cylinder. What is the volume in the graduated cylinder? Include that uncertainty. We've got a 60, we've got a 70. There are 9 lines in between, which means that every increment is 1 milliliter. We're going to divide that in half. Our uncertainty is going to be half, 0.5 of a milliliter. I've got 60, 61, 62, 63. Let's go with 63.5 plus or minus 0.5 of a milliliter. This is good. Can I say 63.514329? I can't. I don't know any of that. Those digits are just silly. They are insignificant. They don't mean anything because I totally just made them up. So when we're talking about our uncertainty, we're also talking about figures, digits that are significant. When we're looking at a measurement like 63.5 plus or minus 0.5 milliliters, I'm going to say that all of those digits are significant. My 63.514329, these guys, they are not significant. They mean nothing. They're not important. They're silly. I made them up. I can't know that. But I can know close to 0.5 plus or minus 0.5. This is the idea of a significant figure. The digits, the numbers within a measurement that actually mean something. There are lots of rules for counting sig figs. They're listed for you on your reference pages. How lucky is that? If you don't have those reference pages out already, maybe pause the video, go grab them so that you can figure out where those rules are. You're going to want to be able to find them because remember that you get to use those reference pages on quizzes and exams all year long. Rules for sig figs, non-zero digits, that's all the digits 1 through 9 that aren't zero. And then zeros that are between non-zero digits are always significant. So the numbers 1, 2, 3, those are all significant. If I throw a 0 in between non-zero digits, that 0 is also significant. Leading zeros, however, are not significant. So if I have something like 0.000410, those leading zeros, all they're doing are holding the other digits in their place values. They are not significant. These are leading zeros. Now, zeros to the right of non-zero digits are significant only if there's a decimal point. This 0 here is to the right of the non-zero digits, and there's a decimal point. That means that this 0 is significant. However, if it was just 410 and there was no decimal point, that 0 to the right of the non-zero digits is now not significant. Significant 0, not significant 0. For numbers written in scientific notation, everything in the coefficient is going to be significant. 2.5 times 10 to the 12th. These guys are significant. We don't care how many zeros there are when we're counting sig figs. Of course, those zeros are super important for the value of the number. But when we're counting our sig figs, only what's in the coefficient, this part, the part that's in front of the times 10 to the something. These are the significant digits. Common logs, we're not going to worry about this until we get to pH when we talk about acids and bases in the second semester. So let's apply these rules and count some sig figs. Literally, I just want to know how many sig figs are in each of these pieces of data. So here I have 45,000 kilometers. I have non-zero digits. Of course, those are going to be significant. Are these zeros significant though? Are they between non-zeros? They are not. Are they leading zeros? They are not. They are zeros to the right of the non-zero digits. Is there a decimal point? There is not, which means that these zeros are not significant. There are only 2 sig figs in this piece of data. How about this one, 45,001 kilometer? Well, significant, significant, significant. These zeros are now between the non-zero digits. That means they are significant. And therefore, I'm going to count all 5 of those digits as being sig figs. How about this number? I've got 4 and a 2. for sure going to be significant. That 0 is between non-zero digits. It is also significant. All of these guys, though, they are leading zeros. They are not significant. So here I have exactly 3 sig figs. How about this value? Almost the same. The only difference is I threw a 0 at the end. Significant or not? We already decided yes and yes and yes. We decided no and no and no. But how about that last 0? It's to the right of the non-zero digit, and there is a decimal shown. That means that that last 0, that 0 to the right, when there is a decimal, is going to be significant. This piece of data has 4 sig figs. Pause the video, or in Edpuzzle, go ahead and figure out how many sig figs in each of these pieces of data. Quick answer check. Because there's a decimal place, these guys are significant. There are 3 sig figs. This one, no decimal, not significant, not insignificant, only 1 sig fig and 500 milliliters. This one, same. There's no decimal place, and so there's only 1 sig fig. Those zeros don't count because they are to the right of the non-zero digit and there's no decimal. But what if I go ahead and throw a decimal at the end of 100 centimeters? Now, because there's a decimal and these zeros are to the right of the non-zero digit, they are significant. There are 3 sig figs. This is saying like 100-ish. This is saying no, 100. How about this one scientific notation? Remember that everything in the coefficient is significant. So 1, 2, 3, 4 sig figs here. Here, only 1 sig fig. 36 zeros, but those don't matter when we're counting sig figs. Only 1 sig fig in 5 times 10 to the 36 milligrams. One of the big challenges in chemistry is calculating with our sig figs. We've got 2 rules. Rule number 1, when we're multiplying or dividing, we're going to count the number of sig figs in each piece of data. Our final answer, whether we multiply or divide, is going to be rounded to the smallest number of sig figs. So let's say that I wanted to find the area of this block, and somebody went out with a super precise, much higher quality measuring device and found that the length was 3.782 milliliters. That means plus or minus 0.00, probably 5 meters. Whereas this one, I don't know, it was like 2. It was like 2 meters. We rounded to 2. So when I multiply 2 by 3.782, I'm going to get 7.564 meters squared. Does that mean that this is so accurate an answer? Do we know that this 2 is like 2.000? We don't. Somebody went out there super ishy, super wishy-washy, and only got like 2-ish. So what we're going to do is we're going to count the number of sig figs. Here there's only 1 sig fig. Here there's 4 sig figs. We're going to round our answer to the smaller number of sig figs. 1 is smaller than 4. So I'm going to have to round my final answer to only 1 sig fig. I'm going to keep that 7. That 5 is actually going to bump that 7 up to an 8. Remember our rules for rounding, 5 and above, we bump up. We're going to keep that unit label. Don't lose your unit label. Our final answer to the correct number of sig figs is 8 meters squared. Because this answer, this measurement was too ishy, our final answer has to also be kind of ishy. I cannot assume that this 2 is good enough for me to say that with confidence. I can really only say 8-ish with confidence. Let's apply that rule a couple more times. Here we're multiplying. We're going to count our sig figs. This value has 2 sig figs. This one has 1, 2, 3. That 0 is between the non-zero digits, so it counts. Which is our smaller number? 2 is less than 3. So we need to round this answer to only 2 sig figs. I'm going to keep 1, keep 2. That 5 is going to bump that 2 up to a 3. My final answer is 13 square centimeters. How about here? I've got 1, 2, 3 sig figs. Here, There's no decimal. That means that the 0 to the right of the non-zero digit is not significant. There is only one sig fig here, my friends. And so 1 is less than 3. We're going to round our final answer to only one sig fig because we're dividing. So I'm going to take that 1. That 7 is going to bump the 1 up to a 2. My final answer to the correct number of sig figs is only 2 hours. How about these last two you do on your own? Quick answer check, 3 sig figs, 2 sig figs. We're going to keep 2 sig figs in our final answer. That 4 is not going to bump that 0 up, so our final answer is going to be 2.0. Don't lose your scientific notation or your unit label. Make sure that those are there. How about here? There's a decimal place, so all the zeros to the right are significant. 1, 2, 3, 4, 5 sig figs. 1, 2, 3, 4 sig figs. 1, 2, 3, 4 sig figs. 1, 2 sig figs. This guy's to the right. There's no decimal. It's not significant. Right now, my final answer only has 2 sig figs, but I need to round to the smaller of the number. And 4 is smaller than 5. I need 4 sig figs in my final answer. I only have 2. How do I turn 160 into 4 sig figs? We're going to add a decimal. So I'm going to keep that 160. And now this 0 is significant. I now have 3 sig figs, but I need 4. I'm going to throw another 0 in there. I now have 1, 2, 3, 4 sig figs, which is what we need. Don't forget that unit label, cubic millimeters. That's our final answer. All the problems that we have done so far, we're multiplying and dividing. That rule number 1, count your sig figs, round to the smallest number of sig figs. Here's rule number 2. When we add and subtract, this one's worse. I'm going to go ahead and apologize in advance. It doesn't make a lot of sense in words. I promise it's better once we do a couple practice problems together. When we add or subtract data, what we're going to do is figure out the place value of the last significant figure in each piece of data. And then we're going to round our final answer to the largest of those last place values. What? Let's do one. So here I'm adding, so I'm going to figure out my place values, place value of the last sig fig. This 5 is our last significant figure. It's in the tenths, hundredths, thousandths place. I've got a thousandth place. Let's look at this one. I've got a 2 is going to be my last sig fig. I've got tenths, hundredths. So we've got the 100th place. Which one is the largest of those place values? Is a thousandth or a hundredth bigger? If I have a pie and I chop it up into 100 pieces, and I have a pie the same size and I chop it up into 1,000 pieces, which one's going to have the bigger pieces? 100th is larger than 1,000th. Therefore, my final answer needs to be rounded to that largest 100th place value. So I'm going to find tenths, hundredths. I'm going to round to the hundredths place. That 5 in the thousandth is going to bump the hundredths up to 6. My final answer is going to be 12.86 meters. Let's practice that some more, because again, this one is a little confusing. So here we're subtracting. What we're going to do is figure out the place value of the last sig fig for each of our data points. So here's last sig fig, it's in the tenths place. Here's last sig fig, it's in the tenths, hundredths, thousandths place. What's bigger, tenth or thousandth? It's going to be the tenths place. So I need to round my final answer to the tenths place. There it is, that 0 is going to keep that 5 of 5. Final answer, 11.5 grams. Let's do another one. You're going to love this one. Let's find the place value of the last sig fig for each of our pieces of data. So I've got a tenths place, I've got a ones place, and I've got a... Are those zeros significant? Is there a decimal? There's not. You know what that means? Our only sig fig is in the hundreds place. What's the biggest? Tenth, ones, or hundreds? Yeah, it's the hundreds. So that means that we're going to have to round our final answer to the hundreds place. What? That 2 is going to leave that 2 a 2, and so we still have 200 milliliters? How does that make any sense? I had 200, and then I added, and then I added. thing is, this 200 is telling me 200-ish. So I had a beaker and it had about 200 milliliters in it. And then I added a little more and a little more, a little more and a little more. It's still only about 200 milliliters. Crazy sauce, right? Okay, next two on your own. Quick answer check. And this is the end of our video lecture, my friends. So here we have an 8 in the tenths, hundredths, thousandths place. Here I have a 6 in the tenths, hundredths, thousandths, 10,000ths place. What's bigger, thousands or 10,000ths? It's going to be the thousandths place. So we're going to round to the tenths, hundredths, thousandths. That 4 is going to leave that 7 a 7. Our final answer is 23.997. MOL is moles. Make sure that you're keeping your unit labels. Last one. This 0 is significant because it is to the right of a non-zero digit and there's a decimal. So I've got tenths, hundredths, thousandths. How about this one? Here I've got tenths, hundredths. How about this one? I've got tenths, hundredths, thousandths. 10,000ths. What's the biggest? It's going to be that hundredths place. So I'm going to round to the hundredths place. That 9 is going to turn that 3 into a 4. Final answer 0.04 meters. And congratulations, my friends, you have finished the very first honors chemistry video lecture. You did it! Let's make sure that you know these things that we want you to know. Make sure that you understand uncertainty and measurement, that plus or minus that tells us the ishiness around a measurement. Make sure that you can express quantities with significant figures and uncertainty, and then also apply those rules of sig figs. Remember that we have two different rules, one for multiplying and dividing, and a different, somewhat more confusing rule for adding and subtracting. Great work today, my friends.